Okay, g'day all. Welcome to another video. So today we're looking at one of, I think anyway, the most interesting fields of study. It's the field of computability, and we're talking about one of the most famous problems from the field of computability, the halting problem, it's called. Okay, so just a little warning, I guess, first. This is not going to be a succinct introduction. I really like this problem, and I've looked at it quite a bit. And yeah, we're going to have a pretty in-depth look at it. And if you find that this video isn't for you, there's plenty of other videos out there that will explain it a little bit simpler and a little bit more succinct. So go and have a look at those if you'd prefer. Okay, so the problem itself, we're going to be studying the problem in terms of functions, since, you know, I'm not personally an electronics engineer. I happen to be a programmer more than anything, so I'm used to describing things in terms of functions, so that's what we're going to do. And this is the halting problem in terms of functions. Write a function, does x halt, that's the name of your function, does x halt, which takes a function pointer as a parameter, or just another function really, it doesn't have to be a pointer, but it takes another function, x, as an input, and it also takes an input for x, I. Okay, so what it's got to do is determine if x halts with the input I. And does x halt must be able to decide if any arbitrary x halts with the input I. Yeah, so it's got to tell us honestly, yes or no, does x halt or does x not halt with the input I, for all possible x programs that we could write, or all x functions that we could write. Okay, but first of all, what in the world is halting? So in modern computer programming terms, a function that halts returns a value. Yeah, it stops at some point. It completes its calculation and returns an answer after some finite amount of time. So it could be a long time, it could be a short time, but the function finishes its calculation with the input I and returns a value. Okay, so on the other hand, a function which doesn't halt enters an infinite loop somewhere. Somewhere in its execution it starts a loop, and it's theoretically never going to leave that loop. It'll just keep going round and round in circles, and it'll never give us an answer. So a few simple examples of infinite loops are, the top two here are C-type languages. So while true, that's an infinite loop. The CPU will just read that and go round and round in circles forever until you know, the silicon dies and your computer turns to dust. This is another one down here, an infinite loop with a for loop. So for and then semicolon, semicolon. Yeah, that's an infinite loop. This one's probably my favorite. So this is old BASIC. Yeah, maybe GW BASIC, or one of those old BASICs, the early BASICs that had line numbers. Yeah, something like this. You can get t-shirts with this. It's pretty cool. So 10, go to 10. Yeah, so the CPU will come along, it'll read this line, 10, it'll say, well, I better execute the statement. And what does it say? It says that the CPU is to go back to line 10. Yeah, so it just goes round and round in circles. It never finishes. In theory, that never returns a result. Okay, so a function which goes into one of these infinite loops, and they can be a lot more complex than this. This is just the simplest examples. A function which goes into one of these infinite loops never stops, and it's called non-halting. Okay, so we want to know if the function x has one of these infinite loops, or something more complex, but you know, that leads round and round in circles, or if it actually finishes calculating at some point and returns a result. Okay, so it seems fair enough. The halting problem asks us to write a function which determines if another function will halt or not. The prototype's going to look something like this. Bool does x halt, function x and input I. And it's going to determine if x halts when executing with the input I. It's going to return true if it decides that the function x does finish calculating a result. And it's going to return false if it decides that actually the function x has an infinite loop and it's never going to return a result. Okay, so it seems fair enough. That's our objective there. Does x halt? Just like that. So let's just have a bit of a go, shall we? Whoops. What we might try and do, this is probably one of the simplest ways to do it, and I think when you're programming you do this quite a bit. To determine if a function x has gone into an infinite loop, what you can do is just run x and wait for a while. Yeah, simple as that really. So my does x halt function might look something like this. It runs x, it waits for 5 minutes, and if x has halted and returned a value, then our does x halt function returns true. Stating that x obviously isn't in an infinite loop since it finished its calculation. Okay, but otherwise, after 5 minutes, if x is still chugging through something, it's probably in an infinite loop. So does x halt returns false. Fair enough. Okay, so the trouble with the previous slide might be obvious. X might still be calculating after 5 minutes, but it mightn't actually be in an infinite loop. Maybe X has got a really complex problem to calculate and it actually takes 10 hours. But after 5 minutes, our does X halt function is going to return the wrong result. It's going to say false, X entered an infinite loop, when actually X didn't. It's just got a complex calculation to figure out. Okay, so in fact, X might halt after 10,000 years. Clearly we can't write does X halt in this way and be sure that we're going to get the correct answer in any practical amount of time. We can't make does X halt just wait for 5 minutes or 10 years even. It's not going to work since X might have a really complex thing to calculate. Okay, so we might get around that. There's a way around that. We might actually let X run indefinitely. So instead of selecting some amount of time to wait, we might just run X and wait for it to finish. Something as simple as this. So run X and pass the parameter I and wait for X to finish. And when X is done, return true. Well, the problem with this is twofold, really. I think, if anything, this is even worse than our previous attempt. This function here never returns false. Yeah, it never returns false. It only returns true when X finishes. We're still stuck in the same boat, so we could be waiting for 50 years for X to finish. X might still be running after 50 years, and we're still, we don't know if X is calculating something or if it's in an infinite loop. X could actually run for a millennium. We have no idea. We'd be pretty happy if does X halt just return true, but there's a good chance that it won't, depending on exactly what X is doing. Okay, so I think the question that we've got to ask is, how do we know that X has hit an infinite loop? So the problems with the previous solutions are that if X enters an infinite loop, we don't actually know it. We're just stuck here, waiting and watching a screen, waiting for does X halt to return, with no indication as to whether X has actually entered an infinite loop, or if it's just calculating something difficult. So what we need, I think, is a way of knowing the difference between X being in an infinite loop and X just taking a long time to calculate something. Okay, so that's what we'll look at. I think the trick here is to write a function that checks states. Yeah, so a function in a finite state machine is itself an emulation of another finite state machine. If you're not familiar with the term finite state machine, maybe just check out Wikipedia or something, but it means that if you create a machine that's only got so many states, then it can emulate other machines with so many states, but the point is that the number of states that it can possibly have, every variable that it's using can possibly have, the number is finite. It might be large, but it's finite. Okay, so there's only so many different states that a function's variables could possibly be in. And if you think about it, if a state repeats itself exactly during execution, then the function will never ever return. So we don't have to wait for X to return to know whether it's actually gone into an infinite loop. All we can do is find a repeated state. If X ever repeats its state more than once, any state at all, then we know that X is doomed to go back to that state over and over and over again. Yeah, just ad infinitum. So I think what we should do is create a list of states. I'll call it state list. It'll start empty, but as we execute X, we want to check against this state list if X has been to that state before. Okay, so something like this. It's a little bit more verbose, but stick with me. This is going to work. Okay, so we could try to save the state of X as it executes. And if it ever reaches the same state twice, yeah, we know that it's doomed to loop. Okay, while there is a line in X to execute, so I've somehow managed to, execute X one line at a time. The details don't matter, it's just pseudocode. But while there's a line to execute in X, I want does X halt to execute the next single line. So it's going through step by step of the code in X. I'm going to let S equal the state of all of X's variables. Now that's actually the state in a slightly more a slightly fuller sense. That's including all of the things like the instruction pointer or the program counter and all of the other internal registers. So it's the complete list of X's variables and all of its registers. It's the entire state. Anyway, if our state list contains S already, then we know that X is going to just, keep going back to S over and over again. It's going to keep generating that state. It doesn't matter how many instructions are between the occurrences of S. X is doomed. So we can return false. X has run into an infinite loop. Otherwise, we can add S to the state list. And eventually, if X actually finishes its execution, then we can obviously return true. It hasn't entered an infinite loop if it actually finishes its execution. Okay, so I think that the biggest problem with this method here is that these states might actually be quite large. So X itself might actually have a lot of variables. It could have like megabytes or gigabytes of variables. And for each one of these states, we've got to save those gigabytes of variables over and over and over again. So even for a few million states, this state list just here, might become extremely large. Let's tackle that. Let's have a look if we can get around that. So this is a slight diversion, but I think it's interesting. So X might have a lot of states, and we don't actually need to save them all. We can use a really, really clever trick. So this one comes straight from a solution to a common programming job interview question. The question runs something like this. Given a linked list, you have to write an algorithm which determines if the linked list has a loop or not. Sounds fair enough. I added this bit at the end because I don't think that the original question is quite worded right to allow the answer that the people are usually looking for. But your algorithm has to run in a linear running time, that's with regards to big O notation, and you can traverse any and each particular item in the list up to and including 3 times, but no more. Okay, I think that's right. The point is basically you've got to find a loop in a linked list. Yeah. Or return that the list has no such loop. Okay, so the solution, if you've not actually done that before, give it a shot, because this is a really interesting solution. I didn't come up with this. Yeah, I didn't come up with this. I just read it somewhere. It's very clever, though. Okay, so the solution is ingenious. It's rather counterintuitive, and I wouldn't mind betting that no human in the history of job interviews has ever conceived this solution on the spot without having read it first. They might have. It's not impossible, but you'd have to be pretty switched on, I tell you. Anyway, here's the trick. You make 2 pointers to traverse the list, pointer A and pointer B. And each iteration of the loop, you increment the A pointer to the very next element in your linked list, but you increment the B pointer 2 elements at a time. Okay, so if there's no loop, B will eventually reach the end of the list. Fair enough. If there's no loops at all, B's actually going to get out of the list. It's going to read all of the elements and pop out the other end. But this is a bit weird. If there is a loop, then A and B will eventually point to exactly the same element. Now, I was so surprised when I read that. I just said, no, surely not. What? I don't think so. And after cursing for a good two hours or so, I decided what I would do is write it out on a piece of paper. So I drew up a bunch of nodes with arrows sort of indicating a linked list. Some of my linked lists had loops and some of them didn't. And I actually got A and B pointers stepping through just with a pencil and paper. And sure enough, it works out. It's very, very clever. It's very clever, but if you need some convincing, just try it out on paper. It's a good exercise. Anyway, that's an interesting solution to an interesting question. And rather happily, we can do exactly the same thing with our doesXHalt function. So what we're going to do is execute the function x with its input I with 2 threads, A and B. And each iteration of a loop, we want to execute 1 instruction with the A thread and 2 instructions with the B thread. Fair enough, so it's the same as our linked list solution from the previous slide. What we want to do is save the states A and B to S1 and S2, these state variables, and if there's an infinite loop, S1 and S2 will eventually contain exactly the same state. Yeah, okay, so that's all we've got to do. We've just got to check if S1 and S2 ever contain exactly the same info. And here's a bit of pseudocode. Yeah, so let A and B be threads to execute X. That's very pseudo, that code. I don't think there's any language, anything like that. But pseudoness aside, the next line, while there is a line to execute in BI, execute the next single line of AI, execute 2 lines of BI, let S1 be the state of A, let S2 be the state of B, and once again that's the complete state, all of the variables and all of the internal CPU registers and that sort of thing. But if S1 ever equals S2, so if those 2 states ever have exactly the same data, then we know that X is doomed to an infinite loop, and return false. X doesn't halt. Otherwise, if B eventually gets to the end of its code, then return true. There you go, and we don't need to save millions of states to RAM, we only need to record 2. And hey presto, we've done it. Okay, so that was fantastic. So we can actually cleverly use a technique for runtime state checking, which very quickly finds any X in an infinite loop. And we can do this in such a way that it actually conserves RAM, and thus simply and economically solve the question of writing does X halt. And you know, basically, yay for us, and we're amazing, and what a fantastic day. So I think I might actually go down and get maybe a bagel and a coffee. Yeah, that's really good. So I might actually test the program first. Hold on. Hold on. Wait. Just a minute. Well, we've written a fantastic and, dare I say, rather clever algorithm. And full of hope, we execute our new does X halt with a particular X and I, and we wait. We wait 10 minutes, and nothing. We wait an hour, nothing. We leave it running for weeks, I get my bagel and coffee, months, then years. It doesn't give us a true or false. X hasn't halted, but neither has it repeated a state. We're sitting here looking at a blank screen waiting for does X halt to tell us if X is in an infinite loop or not. We're in exactly the same boat as we were before. Well, we could check our state checking algorithm for 100 million millennia. X mightn't halt. Yeah, does X halt might not return a value. What's even more disconcerting is if I turn the computer off and decide to try another X and I test, this time something even worse happens. Does X halt returns a value immediately, triumphantly stating true. The program X will halt, and very quickly. So I execute X, and much to my dismay, what happens? X doesn't seem to stop. Does X halt returned true so quickly? I'd figured maybe X had an infinite loop or something straight away, or had, halted straight away and returned a value. But X doesn't return a value. Not only that, it doesn't seem to stop at all. Will it ever stop? Has does X halt lied to us? How can it? So what have we for our efforts? Well, we're still sitting here looking at a blank screen. We've run does X halt with a few X's, and not only do we not know if the function X halts or not, but it seems, rather strangely, like our does X halt algorithm is somehow lying to us. What in the world is happening here? We've got nothing for our efforts. We seem no closer to actually designing the does X halt function, and there happens to be a very good reason for that. The problem is impossible. I was yanking your chain the whole time. I'm sorry. I'm so sorry, but that is funny. Okay. In 1936, Mr. Alan Turing showed that the problem is undecidable. There is no algorithm that will always give the correct answer, and such an algorithm can never exist. All of our efforts so far, and any effort we could possibly conceive, is ultimately doomed to failure. Now, this is basically what Mr. Turing said. It's actually nothing like what Turing said. This is very much in my own words, and from a function perspective rather than a Turing machine perspective. But hopefully I get this sort of more or less right. Okay, so we're going to envisage some devilishly clever trickery here. Does X halt takes X and some input parameters. So it tries to figure out if X halts with the input. But let's have a good look at a particularly mean and evil x function and its input. Let's suppose that the input is the doesXHalt function itself. And let's suppose that this is what x does. If doesXHalt, x does x halt, then infinite loop. Otherwise, return. Okay. The first thing that x does is execute its parameter, doesXHalt, with itself as input. And whatever doesXHalt returns, x does the opposite. So if doesXHalt says x is going to loop indefinitely, x just returns straight away. If doesXHalt says that x returns straight away, then x just enters an infinite loop. Okay, so x can check what doesXHalt thinks and do the exact opposite. Now at this point it's important to differentiate between the doesXHalt that me, the user, runs to check if x halts or not, and this doesXHalt underscore x that x calls in order to lie. DoesXHalt can't possibly return the correct result to the user because x checks what it's going to return and does the opposite. Which means that we can't write the doesXHalt function in such a way that it always gives the correct answer. There is no such function and there will never be. Okay, so the first thing that you might think of when you see the previous slide and hear these things for the first time is surely we can outwit this evil x with some sort of base case checking. I mean, it seems logical. Surely we can have our doesXHalt at the very top of its code check if x is going to try and call doesXHalt to trick us. And if doesXHalt sees that x calls its own doesXHalt to lie to us, then the doesXHalt might actually return false. It might say false. X is not going to return because it causes infinite recursion. And theoretically, an infinite recursion doesn't halt. But if the user then tried to execute x after getting that false from doesXHalt, x would know what doesXHalt thinks, and x would immediately halt, proving doesXHalt wrong. And the only other option then is that doesXHalt, the one that we run, must return true to say that x is trying to trick us, and it does halt. It's going to crash with a stack overflow. But our function sees that x is about to call doesXHalt, and it says it's trying to lie to us, and it just returns true. X is going to crash. But once again, when we actually come to execute x, it's not going to return with an overflow. What it's going to do is immediately see what doesXHalt is going to return, and it's going to do exactly the opposite. It's going to enter an infinite loop. You can't beat it. You can't beat it. Anyway, in reality, this if doesXHalt calls x and x calls doesXHalt, then what's really going to happen is you're just going to run out of RAM. You'll have a crash, probably. Yeah, that's infinite recursion with no base case. So something like that, the code is just wrong to start with. And in practice, actually, the halting problem comes up quite a bit. Like, you know, as a programmer, you often come across times when you want to know if your code is in an infinite loop or not. And there are practical ways to know these things, but you just can't do it for every possible function. That's the point. Okay, so the conclusion remains. Problem. Write a function, doesXHalt, which takes the function pointer as a parameter x and some input for it I, and which determines if x halts with the input I. doesXHalt must be able to decide if any arbitrary x halts with the input I. The only correct answer is no. See you later.